Hello and welcome to episode 26 of Sam-Splaining Science. I'm Sam, I'm your host. I'll be Sam-Splaining the science. Today we're talking about outer space, and we'll be talking about the amazing recent advancements in space exploration. Let's get into it. Hi everyone, how are you? How's it going? I hope you're all doing well. I'm coming to you from my living room floor. The first video episode that I had, which was last week, if you missed it, I took it very seriously, and I was like, I'm gonna have a ring light, I'm gonna have like a very clear background, and this time I'm like, I'm gonna sit in front of my couch. Not on my couch, in front of my couch. But hopefully this makes it a little more casual, a little more like we're just friends hanging out, chatting about space. But yeah, if you missed last week's episode, just so you know, there's a YouTube channel now for this podcast. If you go to Sam-Splaining Science on YouTube, you can find the full episodes there. Sometimes I have some pictures, especially with this episode. I'm going to have pictures and figures and stuff. So if you're interested and want to check it out, you can find it on YouTube. But of course, it'll always be on the audio platforms as well. And I'll always make it so that you can understand everything with just the audio as best as I can. Maybe not so much for this episode. This episode is very dependent on the visual. So highly recommend checking out the YouTube for this. But anyway, as I mentioned, this episode we're talking about space, and specifically about a recent development in space exploration that happened this week. You might have seen it on social media or on the news that earlier this week, NASA released the first set of photos that were captured from the James Webb Space Telescope, or the jwst. If you haven't seen the images yet, you can check them out on the JWST website, jwst.nasa.gov. It's also in the sources in this episode, so you can check those out there. So I was actually planning on doing this space episode for a while now. It was actually one of my first requests / recommendations for an episode topic from my best friend. Hi, Suya. Back in January when the podcast first started, she said that she really wanted to learn about space. And I was like, I have the perfect topic, but it's going to take a while because I wanted to talk about the James Webb Telescope because it's going to tell us a lot about space. So I thought that would be a great way to answer Suya's question. But the telescope launched from Earth on Christmas Day, December 25th, 2021. And it went up into our atmosphere, into outer space. But it took a while to sort of configure everything and start acquiring the data. So it took over 6 months, about 6.5 months, to get the first images from the telescope. So that's why, Suya, this took so long, is because it wasn't my delay. It was NASA's delay. I was waiting for NASA. But they finally got back to us. They finally gave us the images. So now we can talk about outer space. But yeah, in today's episode, we're going to talk about the telescope, why it's so cool, and then we're going to talk about the images that were released this week. So that brings us to today's questions. So the first question today is going to be sort of addressing a very general question. What is physics / astronomy? Just like sort of the essentials to sort of give us some perspective. What do we need to know in order to understand exactly how cool this scientific advancement is? The next question is, what is the JWST? So we're going to talk about what the James Webb Telescope is made out of, how does it work, why did they build it the way that they built it? Lots of questions within this question. And then the final question is, these are really cute pictures, but what are we looking at? What are each of these pictures telling us? So let's get into it. Question 1. We're going to start by talking about physics and specifically talking about light. So light, as we know it, sunlight, maybe light from a light bulb, it is a form of radiation in which radiation is energy. When you hear radiation, you might think of radioactivity or maybe like radiation as a cancer treatment. But in its like sort of one of its definitions, radiation is essentially particles that have energy. And when we think about light, we think about a light particle. A single light particle is called a photon. And this photon acts as both a particle and as a wave. This is the wave particle duality of light that our good old friend, was it Einstein? I thought it was Albert Einstein. Now I'm not so sure. It might not be. Sorry. But basically, in the physics world, it is well understood that a photon of light, a single light particle, acts as a particle, but it also acts as a wave. So basically, it's like this little speck that bounces along up and down, like in a pattern of like a waveform that you would make if you were drawing an ocean when you were 6 years old, like those like up and down waves. So that's sort of how light travels, right? So little pop quiz, is light a particle or is it a wave? I'll wait for you to answer. The correct answer to that question is yes. Is it a particle or is it a wave? Yes. It's both. Just, quirky little light things. One way that we can characterize light radiation energy is on the electromagnetic spectrum, which is shown here on the YouTube video. If you're not watching on YouTube, you can just Google electromagnetic spectrum and you'll see the exact same image that I'm looking at probably. So not all light is the same. And we can tell the difference between different types of light particles based on the energy that they have. And this energy falls somewhere along this electromagnetic spectrum. And the amount of energy that a photon has is related to the wavelength. So remember, light acts as a wave. It goes up and down and up and down. The distance between two peaks of a light wave is called a wavelength. And this wavelength is related to the energy that the photon carries, where shorter wavelengths have more energy. Shorter wavelengths are a higher frequency, so in a given space, there's going to be more frequent peaks, and that's going to increase, or that means that the photon has more energy in it. Longer wavelengths on the other side of the spectrum have a lower frequency, so in a given space there's less peaks, and that is associated with lower energy. So you might notice that on this electromagnetic spectrum that there's only a very small section of it that is called visible light. That's light that we can see with our own eyes. And this is where we see the iconic, the gorgeous, the lovely Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. And it's in this section where the light is between 400 nanometers and 700 nanometers. So very, very relatively short wavelengths. Nanometers is 10 to the negative 9th meters. So 400 nanometers is 0.00000004 meters. Small. But this is light that we can see with our own eyes. Light that has wavelengths around the 400 nanometer mark appear blue, violet to our eyes. Blue, indigo, violet are all like between like 400, 500 nanometers. Light that is around 700 nanometers appears red to us. And then in between is the spectrum red, orange, yellow, green. So higher or longer wavelength, lower energy light that's visible to us is red. Shorter wavelength, higher energy light that is visible to us is blue. So there's, along the spectrum, there's light on either side of visible light. Visible light is sort of in the middle of the spectrum of light, where light that has wavelengths that are a little shorter than the violet light, so less than 400 nanometers, it has more energy. We call that ultraviolet light. And you might have heard of ultraviolet light from the sun's rays, right? Your sunscreen protects you from UVA, ultraviolet A, ultraviolet B. Don't forget your SPF. So those are all, ultraviolet light rays have more energy than the energy that we can see from the light in visible light. Even lower than that, even like smaller wavelengths with higher energy are X-rays and gamma rays, and those are used in like medical imaging applications. Light that has wavelengths longer than 700 nanometers, now we're going to the other side of the spectrum, those have less energy than red light that we see in visible light. We call that infrared light. Infrared light. And then with even longer wavelengths past infrared are things like radio waves. So radio signals that allow us to hear sound from AM and FM radio have longer wavelengths, lower energy. So the main takeaway from here is that there are light waves that exist, that light carries energy, but we can't see all types of light with our eyes, right? Like if you've ever gotten an X-ray, for example, when you get your X-ray, you don't see the X-rays with your eyes, right? You can only see the picture of the X-rays after it was collected and developed with a special machine, right? Like you don't see the rays coming at you. So the same is true for all light that is not on the visible spectrum. We don't see the ultraviolet rays from the sun hitting us, right? We know that it's there and we can measure it, but we can't see it because it's not in the visible light frame. There's a lot of other interesting things about light that we'll kind of get into a bit later, but a little like quirky, cute thing that light does is because it acts like a wave and a particle, it sometimes undergoes things or like is affected by things called interference or diffraction. So, blocking light, for example, you can like try to block, if you put your hand up to the sun, for example, you can block some light, but then some light sort of goes around. It's diffracted. It's interfered with, it's diffracted. These are all things that sort of physicists, astrophysicists think about and consider when dealing with light, because it is both a wave and a particle. It can things can interfere with the path that light takes, and then that interference can change the way that light acts. So for example, it can shift a wavelength to be longer. That's something that a lot of astrophysicists talk about. I've heard a lot this week that like the universe is expanding, right? And because of this expansion, it causes the wavelengths of light to shift so that they shift with a longer wavelength, right? So something that would normally be a blue light would shift to a longer wavelength and look green, for example, or red. Little things like that. It's the reason why the sky is blue, right? The ultraviolet light from the sun shifts in our atmosphere so that the ultraviolet light shifts a little bit, the wavelengths get a little bit longer, and then it looks blue to us. I think. I didn't fact check that, but from my understanding, that sounds right. That should be a whole nother episode. Why is the sky blue? That probably would have been a better episode to start with. But oh well, too bad. Too bad you're stuck with this. All right, so that's my little spiel about light. So now let's get to space. I'm not going to lie to you all, because I am honest with you always, and I will never lie to you. I really don't know a whole lot about space. Like the electromagnetic spectrum I just talked about, I've learned about that a ton of times. I've worked with radiation. I'm familiar with it. I get it. But space, not a clue. I have no idea. So this section, and honestly from here on out, the rest of the episode should be really interesting because it's like, I have no idea. But I'm going to try to have an idea. So from my understanding, the way that I think about outer space, the universe in which we live, is like, there's us, right? Like you and me right now, we're sitting in wherever we are, in a town, in a city, in a house, whatever. So we're in this city, for example, and our city is in a state, and our state is in a country, and our country is on a continent, and this continent is on a planet, and this planet is in our solar system. And our solar system is one of potentially many solar systems in our galaxy, the Milky Way galaxy. And there are many galaxies in our universe. So it's sort of that progression of like from us to we're on a planet. Our planet is one of many planets in a solar system. Solar system is one of many in our galaxy. Galaxy is one of many in our universe. That's how I think about it. The universe, by the way, was born 13.8 billion years ago. You might ask, how do they know that? I don't know. Somebody told it to me and they said it with enough conviction in their voice that I was like, yeah, okay, got it. But I'm sure that they know, right? They get it. They know how it's the Big Bang. You might be asking, Sam, what's the Big Bang? I don't know. But you know what? I don't think that they do either. And I think that's the whole point of the James Webb Telescope, which we're going to get into in a little bit. It's a hypothesis. It's a theory. They definitely know more about it than I do, though. Anyway, so let's talk about our solar system, right? Here's a picture of our solar system. Just Google picture of the solar system, and you'll see exactly what I'm looking at. So the sun is the star of our solar system. A star is basically a ball of hot gas that's on fire, I think. Hot gas, dust, debris, matter, stuff, right? That's what a star is. It's stuff. It's hot stuff. But then our sun is so massive that because it has so much mass, massive, it has a gravitational pull towards it. And because it has this gravitational pull, these rocks called planets are attracted to it, and they orbit it in a way where they keep a certain distance and they just go around and around the sun. And that's our solar system, right? We have 9 planets. Never forget Pluto. I actually don't know what the consensus is, because for a while they were like, Pluto isn't a planet, but this picture is from NASA, and they have Pluto here. So what is the truth? Anyway, our solar system, so our planets go around our sun, and that's our solar system, right? But our solar system is just one of potentially many in our galaxy, the Milky Way galaxy. So now let's talk about a concept that is of interest, of relevance, And that is thinking about for a second how we measure distances between two things in outer space, right? On Earth here, we can say, oh, you know, this desk is 2 meters from me, or, you know, whatever. You can measure it in meters, but in outer space, things are so far away from one another that there needs to be a more efficient way to measure distance in space. So we use a different measure to measure distance in space, and that measure is called a light year. What is a light year? If you're not watching the video, you you should watch the video. In planning this especially these next like 2 slides in particular, I was cracking up while I was making these. So you just got to watch the video. What is a light year? In astronomy, distances are measured in light years. Just going to take a quick sip of coffee. Okay. So a light year sort of sounds like a unit of time because it has years in it, but it actually is a measure of distance. And what it is the distance, how far a photon of light travels in 1 year. Now, a very scientific factoid is that whether it's visible light or infrared light or ultraviolet light, any kind of light, all light travels at the same speed. And that speed is approximately 3 times 10 to the 8th meters per second. So 3 with 8 zeros after it, or 300 million meters in 1 second. Now, for the Americans who refuse to acknowledge the measurements, the units that the rest of the world uses, 2 meters is around 6.56 feet, about 6 feet, 7 inches long. Do you want to know what else is 6'7"? Do you know who else is 6'7"? New York Yankee legend and 2022 All-Star, Aaron Judge. He's 6'7". He's 2 meters tall, this man. So if we were to clone Aaron Judge 150 million times, which sounds like a dream, to be honest, and we lay all of those Aaron Judges down from head to toe, that is how far light travels in a single second. In 1 Mississippi, that's how far light travels. 150 million Aaron Judges in 1 second. That's fast, right? Now, we know that light travels 150 million Aaron Judges per second. But, I mean, or if you're a little less intelligent, 300 million meters per second. But how far does light travel in a year? So we know that that's how far it travels in 1 second, but how much does it travel in a year? So to figure that out, what we can do is multiply the 300 million meters per second by the number of seconds in a year. And that will tell us how far light travels in a year. So to find out the number of seconds in a year, we take the number of minutes in the year, which we all know is 525,600 minutes. We know that, right? And we multiply that by 60 seconds in a minute to get 31,536,000 seconds in 1 year. Then we can multiply 31,536,000 seconds per year by 300 million meters per second. And then we can find out that light travels 9.468 times 10 to the 15th meters in 1 year. So that's So that's 94608 followed by 11 zeros. So that's million, billion, trillion. 9 quadrillion, is that what comes after trillion? 9 quadrillion, 460 trillion, 800 billion meters in 1 year. That's really far. Like, for scale, Aaron Judge is 2 meters. Aaron Judge for scale. But that's very far, right, in 1 year. So when in astronomy, when we talk about light years, it's like 9 quadrillion meters. Just a second to wrap your head around it. How far that is, and what that means is how huge things are, because we measure things in thousands of light years. So what comes after quadrillion? Quintillion? Huge! So far! The universe is humongous. That's why we use light years, so that we don't have to say, 500 quadrillion meters. It's just, oh, no, it's 5,000 light years, NBD. So yeah, that's why they measure in light years or light minutes and not meters, because meters would be a ridiculously large, long number. But let's do a little more math, because math is fun. I mentioned light minutes. So light minutes is like not as long as a light year, obviously. There's definitely, a minute is shorter than a year. And honestly, you could fact check me on it, but I'm pretty sure that's true. So let's use this sort of knowledge to say how far away is the sun in light minutes, right? So we know from a simple, easy Google search that the distance from the Earth to the sun is 149.6 billion meters. So less than a light year. 149.6 billion meters between the Earth and the sun. And we know that light rays travel at 300 million meters per second, because that's true of all light, including the UV light from the sun, including the visible light that we see from the sun. 300 million meters per second. So in the case of the Earth or the sun, we can say, so if we want to figure out how long it takes the light from the sun to reach Earth, we can do a simple calculation where we can take the distance from the Earth to the sun and divide it by the speed of light, which is 300 million meters per second. And then we can find that that answer is 498.667 seconds from light to get from the surface of the sun to my apartment, which is now 110 degrees because I had to turn off the AC. Great, love it. So 498.667 seconds. If we multiply that by 60, we can get that number in minutes, which is 8.31 minutes. So you might have heard that thing like, oh, it takes light from the sun 8 minutes to get to Earth's surface. But now you know that it's true because we use math to figure it out. So you're welcome. Don't ever say math didn't do anything for you, because that's a lie. It does everything for us. Yeah, so in this case, we can also say that since it takes light 8.311 minutes to travel from the sun to the Earth, we can say that the Earth is 8.311 light minutes from the sun. That's how the measure of distance relates to the time aspect, if that makes sense. Hopefully that example sort of gave some context and understanding as to how we can use light distances to figure out how far things are from each other based on how fast light moves and how long it takes light to travel from one place to another. Okay. But this is like also, this is just within our own solar system, right? So like 8 light minutes, light years, like within our own solar system. But like, what about the distance from us to like other stars in our galaxy? And those stars might be like our sun. There's construction happening next door. That scared the crap out of me. I was like, what the hell is going on? It's construction. Yo, I can't imagine having to do construction right now. It's so hot. Anyway, yeah, so those other stars might be like the sun, and they might have their own planets surrounding them, right? Orbiting them. So how far are we from those other planets? And like, how far are we from other galaxies? Not the Milky Way galaxy where we live in our little solar system, but in other galaxies, right? And what about the distance to the edge of the universe? Like, so far, but like, can we measure it? Can we figure it out? How far we are from the edge of the universe? How old the universe is? Because now we know we can use the speed of light to connect distance and time. So, just so many questions that we can answer with physics and with math, which we love. We love it. And in a way, this is where it starts to get a little trippy, right? Because, like, the light that we're getting from the sun is old. It's 8 minutes old, 8 minutes in the past, right? Because it took these photons that are hitting my skin, that are hitting my window right now, 8 minutes to get here from the sun. 8 minutes, right? So these are old photons from our closest star. So when we think about like, okay, can we see stars further away? The light from the stars that are further away are going to take longer to get here because they're further, but they travel at the same speed. So, and when we see the light from further stars, from further galaxies, that light, because it had to travel farther, is older. So it's like going years away, right? If we measure from right here something that was 1 light year away, what we're measuring is light that has traveled for a year. That's a 1 year old photon, you know? Does that make sense? Did I say that right? I think I did. Like, yeah, if we're measuring something 1 light year away, the photons that we're seeing at this second traveled 1 light year to get to us. So that light traveled for 1 year. It's old light. So what we're collecting is from the past. It's just like trippy time travel. Time travel. It's wild. Crazy to think about. But so cool. So cool. Where's my mouse? I keep losing my mouse. Okay. So that was question 1. A little primer of physics and astronomy and getting an idea of like light and how it acts in the universe. So now we're going to move on to question 2, which is what is the JWST? So the JWST, I'm going to keep calling it that, but the formal name is the James Webb Space Telescope, is NASA's newest deep space telescope. It was launched, as I said, on Christmas Day of 2021. This construction, I feel like you can definitely hear it, and I'm sorry about it, but whatever. If I have to live with it, you can deal with it for freaking 45 minutes or however long this episode. This might be a long episode because it's just a lot to talk about because it's so cool. But anyway, the JWST is not NASA's first ever space telescope. Its predecessor was the Hubble Space Telescope, which you might have heard of. Hubble already told us a lot about our galaxy and about the universe, but as all scientists and engineers do, the wonderful people at NASA took what they learned from Hubble and other experiments in space, and they designed this whole new telescope, the JWST. So Hubble, compared to JWST, was much smaller. The mirror, which we'll get into in a second, is why mirrors are important on a telescope. The mirror of Hubble was about 8 feet in diameter, so about 1.5 feet longer than Aaron Judge. That's really going to be my new unit of measurement, is like Aaron Judge. How many Aaron Judges is this? It's about like 1.1 Aaron Judges. But the Hubble telescope was 8 feet. The mirror was 8 feet in diameter, and it only captured, measured, imaged visible wavelengths, right? So our Roy G. Biv, all of the light in space that is visible light was captured by Hubble. Well, not all of it, but like it was able to capture visible light in outer space, right? But we know that there are other types of radiation, other types of light waves that are in our universe. And the JWST is different from Hubble in that it's able to look at longer infrared wavelengths. It's also much bigger than Hubble, so the JWST is about 20 feet in diameter. So that's like 3.4 Aaron Judges. I don't know if my decimals are right. It's between 3 and 4 Aaron Judges, for sure. So pretty much larger than the Hubble telescope. And that, it being larger, means that even more light energy will interact with it because it's a bigger target. And that means that it can collect more data than the Hubble Space Telescope could. And there are a lot of comparisons this week of the results from the JWST and the results from Hubble. A lot of people are not being nice to Hubble. They're saying, look at how trash this image was compared to the JWST. And it's like, we needed Hubble to make progress. Don't shit on Hubble. We love Hubble. We appreciate Hubble, but we also appreciate JWST. Both can be true. Both can be true. But yeah, so that's how the JWST is different and a little more innovative from Hubble. And one thing I want to highlight that I don't know if I did yet or not is that the JWST, as I mentioned, can measure infrared light. So remember, infrared has longer wavelengths, less energy than red visible light. As light travels through space, the waveform of the light shifts. Because the universe is expanding, it is able to sort of spread out a little bit. That's sort of my understanding of it, and I don't know if that's accurate or not. If you're in astrophysics, you can comment and tell me if I'm wrong. I, again, am not an expert in this, so I probably am wrong. But from my understanding, the wavelengths of light in space are able to shift and become longer. So that means that visible light becomes infrared light as it moves to the right on that spectrum that we looked at earlier. So I think one of the analogies that I saw to it was like when you drop like a water droplet into a puddle or like a pool, the waves of water, like the ripples, get larger as you move further away from the center, and like more spread out as you move away from the center. So sort of like that, like as the universe is expanding, moving away from the center of the universe, the wavelengths can shift and get longer. So because of this, there's a lot of light in outer space that's been traveling for a long time because the universe is very large. And those lights have longer wavelengths because they've shifted. So we need infrared technology to detect those shifted wavelengths. And the JWST incorporates the infrared technology that will allow us to measure those things. So very cool, very exciting. And an advancement over Hubble, who was not able to do those things. Again, no shade to Hubble. We love you, Hubble. Just JWST is a little better. A little. So the JWST mission is between 5 to 10 years was the goal. Although I listened to an episode of the Daily podcast this morning, the New York Times podcast, and I forgot the name of the man who they were interviewing, but he was talking about the JWST, and he said that the launch went so well that they have the resources to expand it to almost 20 years mission, which is wild. I can't think about me in 20 years because I'll be almost 50. Anyway, the goals of the mission of the JWST are really very experimental, right? We want to collect Who's we? I wish it was we. How cool would it be to work at NASA? I'm not smart enough for that, though. But NASA's goal is to collect information about our galaxy, the Milky Way, the stars that are in our galaxy, potential exoplanets or planetary-like bodies that surround these other stars in our galaxy, as well as look at the universe, right? And other galaxies that are in our universe. They also want to learn about how stars and planetary systems are made, how they form, how they die, because stars can burn out, they can die. And they also want to learn about the makeup of atmosphere on other exoplanets, right? These other planetary bodies that might orbit a star like we orbit our sun. The technology on the JWST will allow them to look at the atmosphere of those exoplanets and see how similar it is to our atmosphere, and if there's elements in those atmospheres that are conducive to life. So very cool stuff. So what is the telescope made out of? What does it look like? So on the video here, I have a diagram pulled from NASA, of course, that sort of outlines it's a schematic of the telescope. I mentioned earlier when I was talking about Hubble and comparing the size of Hubble's mirror to JWST's mirror that one of the key components of this telescope is a mirror. Why, you might be asking. So mirrors reflect light, right? That's what mirrors do. So the JWST has two types of mirrors, a primary mirror and a secondary. So the primary is made up of 18 hexagon segments that are smushed together. They kind of look like a honeycomb in shape, and also in color because they're coated in gold. So there's 18 hexagons that are smushed together, and it's about 20 feet in diameter, like I mentioned. And this honeycomb, this large hexagon, reflects light from space, right? Galaxies, stars, whatever, they shine light towards this mirror, and the light reaches this mirror, and then the mirror, the primary... What the heck? It's an 800 number. I'm not home. I am home. This episode is chaos. A little bit of chaos, but it's fine. It's not chaos, it's conversational. We're chatting. We're having a casual chat about science. Right, so these primary mirrors, the big primary mirror is made up of 18 hexagons, 20 feet in diameter. The light from galaxies, from stars, come and it hits the primary mirror, and then the primary mirror reflects that light. And it reflects that light onto the secondary mirror. And the secondary mirror is sort of positioned in front of the primary mirror so that when the primary mirror reflects it back, it goes straight onto the secondary mirror. And then the secondary mirror is sort of angled in a way that the light that's reflected onto it will then reflect back a little bit towards the primary mirror, but it will actually go down into the telescope. And then within the telescope, there's different instruments, which we'll get into in a second, that can collect the data from the light that is being reflected. One other thing that I want to mention is that as an engineer by training, there were a lot of engineering problems that NASA had to solve before making this telescope a thing, right? They knew how they wanted to improve it from Hubble, right? They knew that they needed a bigger telescope. They knew that they needed material that would allow them to measure infrared wavelengths. But in making a bigger, more efficient telescope, they also needed to consider things like the weight of the material, right? Because it was going to be so much bigger, they needed it to be less weight by volume than Hubble was. It needs to be lightweight in order to get a rocket up into space. Nothing can be too heavy. Otherwise, it'll throw off the trajectory of the launch. Also, it needs to fit in a rocket, right? So this telescope was sent up to space in pieces. And then the robot that's on the telescope assembled it in space, right? So there's just a lot of engineering problems that they had to solve in terms of like optimizing space and weight, choosing the best materials and making it the most efficient in order to get this to work. And I didn't want to let this episode go by without acknowledging the difficulty of doing this and having it work the way that it did, which is amazing. It worked amazingly. So shout out to all the engineers. You killed it. All right, but we talked a little bit about how the light reflects from the primary to the secondary mirror. One other thing I wanted to talk about, just briefly, is that on the telescope there is a sun shield. And that sun shield blocks the sunlight so that the light from our own star, which we know and love, doesn't interfere with our ability to measure light from other places in the universe. So it kind of came with its own set of like sunglasses, like its own visor of sorts, which I thought was smart and pretty cool. But okay, getting back to the telescope and like how the light reflects from the primary mirror to the secondary mirror, and then from the secondary mirror into the telescope, where it interacts with all these different instruments. There were 4 instruments that I saw. This is, again, information from the NASA website, and all of the websites that I got all the information from will be in the description. But there were 4 instruments in particular that they highlighted on their website as like being key to JWST's ability to measure what it measures, right? So the first instrument that they talked about was near infrared camera, or the NIR cam. And this camera covers wavelengths in the near infrared part of the spectrum. So near infrared is closer to like visible light. It's like just a little bit longer wavelength than visible red light. So visible red light has a wavelength of like 0.7 microns or 700 nanometers. Those are equivalent. Whoa. It's obvious I did not finish my coffee today. Okay. How long have I been recording? Almost an hour. Yikes! This is gonna be a long episode, but it's cool, right? I don't know. Maybe you're like, shut up. Maybe you already have me on 2x speed and you're like, when is this idiot gonna stop talking? Never. Okay. Right, so the near infrared cam covers wavelengths that are just longer than red visible light. So it's the near infrared just past red visible light. So with this, you can see like cooler red stars with a little bit of a longer wavelength than visible light. And you can also, it takes what's called coronagraphs, which are basically images of an object that is near a very bright object. So like it blocks out the very bright object and then you're able to see what is around it. So like planets that are orbiting very bright stars, we can look at those planets. We, again, who's we? They can look at. Okay. The next instrument that they talked about was the near infrared spectrograph. This is also in the near infrared stage. Basically, what a spectrograph does is it's able to measure diffraction of light, and depending on what the atmosphere is made up of, what the atmosphere is comprised of, the chemical composition, if there's oxygen or nitrogen or water, the diffraction of light will change based on what elements are in the atmosphere. And they can characterize how the light will change based on what chemicals are in the air. So they can use this NIR spec to learn about the chemical composition, the temperature, the mass of an object, in this case, potentially an exoplanet. So if there's light from an exoplanet, they can measure the spectrum to see like what the atmosphere from this planet is made of. Another instrument that is on the JWST is a mid-infrared instrument. And this has a camera and a spectrometer, so similar to the NIR cam and the NIR spec, but it measures in the mid-infrared wavelengths. So a little bit longer wavelength than the near-infrared. And here in the mid-infrared spectrum, they can see planets, dust, so like space dust from stars exploding. They can see that dust in mid-infrared light. So that's another instrument that allows them to see space things. The final instrument that they talked about was called the Fine Guidance Sensors and Near Infrared Imager and Slitless Spectrograph. From my understanding, this instrument is very important in making sure that the telescope is pointed precisely where it needs to be, and that makes sure that it maintains its high quality or obtains high quality images. So all four of these instruments play an important role in providing information that will answer NASA's mission goals, right? Like we can see more in this infrared spectrum. So we can see more galaxies, we can see from further away because it's bigger. But also we can use the spectroscopy to see the composition of planets and the composition of the atmospheres on these planets. So that's very cool and exciting. Now the final question. Cute pics, but what are we looking at? So these are the pictures that NASA has released. If you're listening, you can go to jwst.nasa.gov and look at the first images that were revealed. There should be 5 of them. But if you're watching, we'll look at them together and we'll talk about what it is, what it means, what are we looking at. So the first image that they revealed is what they called deep field, a deep field image. So this picture shows a piece of the universe as it was 4.6 billion years ago, right? So the light that was captured to make this picture traveled 4.6 billion light years to get captured by the JWST. Very, very far. This is a galaxy cluster called SMACS. I don't know if that's how they call it. It's SMACS. I'm going to call it SMACS because that sounds cool. SMACS 0723. And this was taken with the NIR cam, if I remember correctly, if I wrote that down correctly. So it's the near infrared camera. And basically what they did was they collected pictures at different wavelengths along the near infrared spectrum. It took about 12 hours to collect all these images, and then they compiled it, they smushed it together. The same picture with Hubble, not to bring Hubble back into this, but the same picture of this subset galaxy cluster with Hubble was not as defined, and it took weeks to collect. So this is much more detailed, much better resolution, and it took only 12 hours. So this just shows like how much of an improvement JWST provides to NASA because of its efficiency and because of its ability to pick up very small galaxies that are very far away that Hubble couldn't. So yeah, this square image is representative of a chunk of the universe that would be equivalent to the area of a grain of sand if you held it in your hand and held it at an arm's length. So like if your whole field of vision was the universe, this picture would be the size of a grain of sand held at an arm's distance in your field of view. So what that means is that this is such a minuscule percentage of the total universe that's out there. And an important thing to talk about is that every single one of these little specks here, even the smaller ones, are galaxies, right? So each of these galaxies, there are thousands, they said in this picture, thousands of these light specks. I mean, some of them look so cute. Look at this one. So cute, little swirly twirlies. Look at this one. Gorgeous. I love this picture. But every single speck here is a galaxy, right? And each of these galaxies might have one or more sun-like star, which may have one or more planets orbiting it. And those planets orbiting those sun-like stars in those galaxies, of which there are thousands in this speck of sand, those planets could be habitable. They might be just like Earth. They might have running water. They have faucets there. No, they might have like liquid water. They might, have organic compounds that allow sustainable life. In one of these little specks, in any of these little specks. So I don't know. I just look at this picture and I'm like, yeah, there's no way. There's no way that we are the only beings. There's no way that we're the only planet that can sustain life in this universe. Do you see how many? There are 1,000 in a grain of sand. There's no way. I'm blown away. I love this picture. It reminds me that I am so insignificant and nothing matters. but not in like a sad way, in like a, nothing matters, like a refreshing sort of like anxiety reducing way of like, oh yeah, nothing matters. These could all be parallel universes, you know? You know how people talk about that? Like, oh, in a parallel universe. Like in this universe right here, maybe I'm married to Chris Evans. Can't say no because you haven't proved otherwise yet. All right. One other thing that I want to talk about here, because the first thing that I saw when I looked at this picture were these like star-looking things, and they have like these spikes. I don't really know how to describe it. It looks kind of like a snowflake. I don't really know how to describe it. It looks like a snowflake. It's got like 6 points to it. Look at the picture, you'll know exactly what I'm talking about. But these are what's called, I lost it in my notes. Diffraction spikes. So they happen when light interacts with the primary mirror. So remember those like gold honeycombs, and the beams that hold the secondary mirror. So Hubble has those diffraction spikes too, but they look a little different because the mirror configuration on Hubble is different than it is on JWST. But basically they're there because of the way that light interacts with the telescope, and it makes bright things like explode a little bit. But yeah, the Hubble diffraction spikes only have 4 spikes, I think. JWST has 6. So that's how you can tell them apart. If you can't tell them apart by the superior quality of the JWST, you can use this diffraction spikes to determine which telescope took the picture. Just a fun fact. One other thing that I want to talk about here is another thing that I noticed when I first looked at the picture is that some of these galaxies look a little warped. They look a little like shooting stars almost, right? And I watched one of the NASA press conferences, I guess. They like interviewed people who work at NASA and like talked about the pictures. And one of the women said that one of the women who they interviewed said that these are warped, they're stretched out because there's a cluster of galaxies that are nearby, that are around it, that have lots of mass, right? They're massive. And this mass distorts the space-time, which I absolutely understand exactly what a space-time is. I don't. It sounds like science fiction, but my guess is that it's like space-time, like space and time. I don't know. I really don't know. But she said it distorts the space-time so that the light that is traveling from those galaxies that are behind the massive objects get distorted so that it's like bent towards us. So like I'm looking at this, it's sort of like in the top, I don't know, on the video you can see what I'm pointing to. But like one of the galaxies is sort of warped around this bright looking galaxy. And I'm guessing that like this warped one is like behind the massive bright galaxy, and that's why it looks sort of bent. I don't know. Again, if you're watching this and you're an astrophysicist, first of all, I'm sorry. I think if you're watching this and you're an astrophysicist, you turned this off a long time ago because you're like, this girl has no idea what she's talking about. True. But if I'm saying something incorrectly, or you can elaborate on something that I'm saying, you can tell me about it in the comments. Because I want to learn, I want to understand, I just can't. All right, so that's the first picture. This is going to be a long episode. But I think it'll be worth it because I just think it's so cool. Okay, this is the second image that NASA released. It is a spectrum analysis of the exoplanet WASP-96b. So WASP-96b is 1,150 light years away from Earth. It is in a constellation in our sky called Phoenix. And WASP 96b orbits very close to its sun-like star. So sort of like Mercury is the closest to our sun. WASP 96b is very close to its sun-like star. And this exoplanet is made up of mostly gas. But here we see a spectrum of the gas on this planet. These peaks that are shown as a function of like the light and the way the wavelengths change with the light are sort of characteristic of H2O, of water, right? So basically what this spectrum analysis is telling us is that there is water vapor on WASP 96b, which is amazing. Like, we know that water is necessary for life. So astronomers are really interested in seeing if there are planets that have water, specifically liquid water, but if planets have water that can sustain life. Life also needs organic compounds like carbon-containing things. Like for us, we need glucose, which has carbon in it. So with these sort of spectral analyses, we can see characteristics of, what's the word I'm thinking of? Like elements that are necessary or byproducts of life, which is pretty cool. Another condition for looking for life on other planets is like temperature, right? So if a exoplanet has water, like WASP 96b has water vapor, if it's too close to its sun-like star, and that sun-like star is very hot, that means that the surface of that planet will be very hot, and that water will more likely than not exist in its vapor form compared to its liquid form. And liquid form is needed to sustain life, right? So if a planet is a little further away, maybe it's too cold, and the water also doesn't exist as liquid, it exists as a solid, as ice, right? So there's sort of this like Goldilocks region of like not too cold, not too hot, just right. Water exists as a liquid. And that could suggest that life can exist there. It is a habitable planet in that case. Okay. But yeah, so this shows that the JWST can allow us to look at the spectrum of compounds on other planets to tell us whether life exists elsewhere or not, whether we are alone or not, which is so cool and terrifying at the same time. Okay, third picture. This is a picture of a planetary nebula called the Southern Ring Nebula, or planetary nebula NGC 3132. This is a star that is approximately 2,500 light years away. So the image, the light that was taken from this image traveled for 2,500 years, which means that we got this picture, so that this picture is like, what, 400 BC? I don't know what was going on in 400 BC, but this was going on in 400 BC. Which is pretty crazy. This is a picture of a dying star, and they took the same picture with two cameras. So one is sort of like a bluish center with like a red flame-looking thing on the outside, and then the second one is sort of reversed, where you see the interior is red and the exterior is blue. So if we look at the picture with like the red center, the blue ring around it, we can see there's actually two stars in the center of this nebula. And from the NASA Q&A that I watched, my understanding is that one of these stars is dying, and that's what's causing, as the star is dying, it's like releasing all of this gas and all of this dust, and it's been doing so for thousands of years. And there's another star next to it that's just sort of like chilling. And it's like this stardust from the dying star will pass this second star, but it won't affect it in any way. It won't kill the other star. It won't make it it's just going to sort of pass by it, the space dust. But yeah, this is a beautiful picture. And I think the cool thing is that we can see that there are two separate stars in the center with this near infrared technology that we didn't have previously. We didn't have this sort of resolution with Hubble. So this is really cool, really exciting, beautiful picture. The fourth picture that they released is a picture of interacting galaxies called Stephan's Quintet. The NASA website told me that this group of galaxies was the group of galaxies that was featured in It's a Wonderful Life, which I know exactly what they're talking about. If you've seen It's a Wonderful Life, it's in the beginning when like Clarence is talking to God, I guess. That was wild to me. I was like, I thought they just drew that. I thought they just made it up. I didn't realize that it was like a real place in our universe. But yeah, Stephan's Quintet. Anyway, hey Clarence. So to get this picture, JWST used the infrared camera to pick up the near infrared spectrum. It has a better resolution than the image that was taken with Hubble, and a lot more detail. And we can see that there's some space dust. Well, first of all, two of the galaxies are very close together. They're practically interacting with one another, which is very cool. And we can see that there's like space dust and gases and stars that are interacting and sort of being pulled from some of the galaxies because there's such a gravitational pull on them, on one another. Just a beautiful vision. And this picture is 290 million light years from Earth. This picture is 290 million years old. And honestly, it doesn't look a day over 289 million. So that's pretty amazing. I'd love to know its skincare routine. Gorgeous. The last picture is my favorite picture. It's so beautiful. It's the background of my phone because it's just so beautiful and I love it. This is the star forming region in the Carina Nebula, the NGC 3324 in the Carina Nebula. Carina Nebula? I don't really know how it's pronounced, but for some scale here, the tallest peaks, so this basically, it looks like a mountain range of sorts, right? But it's actually clouds of stardust, where the tallest peaks here are 7 light years tall. So it takes light 7 years to get from this peak to this valley. Humongous. And yeah, so these are just gaseous formations, mountains that are around the star forming region in the Carina Nebula. So this, instead of looking at the death of the star, like we did in the Southern Ring Nebula, here we're looking at stars being born. And this one is actually just a short 7,500 light years from us. So really not too far compared to the 290 million of Stephan's Quintet. But just stunning, beautiful. And you're just like watching stars being born. It's beautiful. I love it. I love it. It's so cool. Yeah, but that is the 5th and final photo that NASA released from the initial 5 that it captured. And I think the overall tone from NASA is one, they're just ecstatic that it worked this well. You know, there's always places where things can go wrong. and some things you can plan for, but some things you really can't control, right? Like once it's up in space, you can't bring it back down and fix something, So if something goes wrong, it's, very difficult to overcome that. But NASA did an amazing job. They got it up there, they got the data, and not only were they able to get the data, but look at it. Look at it. Stunning. Better than I think anyone could have imagined. So just really exciting. Again, I'm not an astrophysics person. I'm not an astronomer, but I wish I was. This makes me wish that I was, because it's so cool. It's amazing. And I'm very happy for everyone who's involved. I'm happy for us as a human species that we get to learn more about what's out there. Just a lot of fun. Just wonderful, incredible things. I love science. Crying because I love science so much. But yeah, I guess this is the first image again. This is the first image of the deep field space image. I guess it's time for the take-home messages for this episode. And I guess my take-home messages are there's no way that we're alone in this universe. And I guess coming off of that, stay humble, right? My issues are nothing because look at what's out there. So just always keep that perspective in mind of like, wow, you are so insignificant. And not in a mean way, not in like a, don't bother trying to do things because nothing matters. But it's like when you're up in your head about things like, oh my God, this is happening, blah, 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 nothing matters. Nothing matters because this grain of sand has more galaxies in it than problems that you have in your life. So just remember that. Beautiful. I love it. All right. Enough with the existential stuff. That's all for this week's episode. Please don't forget to follow, rate, and review the podcast wherever you're listening. You can also subscribe on YouTube, please. If you prefer to watch your podcasts, I think this is a good one to watch because there's a lot of figures and images. You can also follow the show on Twitter and Instagram at sam-splains. So connect with me there and ask questions if you'd like. You can also submit your questions to samsplainingscience.com/ask. So if you have any questions you want Sam explain to you, ask away. Thank you very much for listening to this week's episode. I hope you learned a little bit and laughed a little bit, and I will talk to you next week. Bye.